Okay, so let's see here. We need a calculator here. I want this one. So let's just review what we were talking about last time. We're talking about the directional derivative, and we said that if you have some surface, some function, and we could consider, we could consider a point on that function, and then think about from that point going a certain direction, or in other words, some proportion of changes of x and y would be equivalent to going in some direction from that point. So and so this is the idea that we're going to head in some direction, horizontal direction, which is comprised by a change in x and also a change in y simultaneously. Okay, and so then when we do that, we want to look at the rate of change, resulting rate of change in the direction that we pick. So we started with, before we did all this, we said there were two rates of change. Here's one of them, right? What rate of change is this? What do we call this one?
Ez over dx.
Yeah, yeah, you call it, yes, the partial, partial of z with respect to x. So this one is partial of z with respect to x. Okay, or this was the function I called h, so this would be h sub x at the point, and in this case this was the point 2, 2. And there it is, 2, 2, 2, 2. Okay, and so just looking at this graph, can you tell whether that would be positive or negative, that partial derivative? If you go in the x direction, what happens to z? That you can see that by looking right down the trace on the surface. Z goes down. And we actually found it last time. We said it was negative 2. We took the function h, we found the partial derivative, and we plugged in 2, 2, and we got negative 2. And then there was the other, when we first started talking about partial derivatives, there was this one. And what is this? What derivative are we talking about here?
H sub y, right?
This is right, in the y direction. So yeah, when we first started talking about the calculus of these multivariable functions, this is what we talked about. Two rates of change. A rate of change in the x direction, and a rate of change in the y direction. What about this one, the y direction? Negative or positive or about 0?
Negative.
Negative. And this one we calculated as, we actually got the value last time as negative 1. Okay, but then we transitioned, and we were working with these partial derivatives, and we transitioned to the idea that really there's more rates of change than that if you allow combined changes. If you allow x and y to change simultaneously, there you could get lots more rates of change than just these two. And that's the idea of the directional derivative. So for instance, here in the second quadrant, something like somewhere around 5 pi over 6. Maybe right there. So here is a different direction which represents a combined change of x and y. So maybe this is something like, x change of, I don't know, 1.5 to a y change, or negative to a y change of 1, right? So there's this proportion, this direction is some proportion of changes, negative 1.5 in x to positive 1 in y, and go in that direction, and there's an associated rate of change of our surface with that. What is this one, positive, negative, or 0?
Increasing both x and y.
No, so the x and y taken together are at a proportion, so dx to dy is negative, I'm just saying this, negative 1.5 to 1. So this looks about like that. Or maybe like -3 to 2. That's the same thing, -3 to 2. And as a result of that combination of changes, there's a rate of change of this function. There is a rate of change. And so that rate of change is the change in z with respect to a horizontal change in that direction, or a proportion of changes -3 to 2. And is that rate of change positive, negative, or 0?
Would it be negative?
Negative, going this direction. How does z change on the surface, the gold surface? Does it go down? Does z go down?
No. Positive.
Z goes up, right? Z goes up. So for a change along that trajectory of this proportion of changes in x and y, z goes up. And maybe this is close to a rate of change of 1. For every 1 unit you go horizontally, z goes up by 1.
So then it's just based on the axis, the direction that it's going, it'll determine whether it's positive or negative. You're just looking at where it's going based on the x, y, z coordinate system, right?
The direction is a two-dimensional phenomenon. It's horizontal.
Right. So
then the rate of change is three-dimensional, right? The rate of change is the change in height, or the change in z, per change along that horizontal direction. It's how much the surface goes up per horizontal change in the direction you picked.
Okay, so as you're going that way, then it's changing depending on which, because you have the tangent plane, I guess, right here, right?
This is a vertical plane that contains the direction of u.
Okay.
And so that vertical plane is then showing us a trace on the surface that's going to give us that rate of change, which is positive, because you go up. If you're on the side of a hill and you walk in this direction, you would be walking uphill like this. Therefore, this directional derivative is positive. Does it make sense?
A bit more, yeah, because okay, so I get it now.
Okay, cool.
Thank you.
You bet. Okay, so that's kind of an overview of what we talked about last time. So
things really fast. Like I think I'm already halfway done to 25. So, like.
Isabella, your microphone is on. Isabella. Okay, so this kind of begs the question: if we have all these different rates of, so we no longer have just two rates of change. We have a rate of change in every direction, which is like an infinite number of rates of change now that we can talk about. So let's see that. So you're looking at, so as we change that direction, we get a rate of change in every direction that we could pick from that point to 2. Okay, so there begs a question: of all those directions, what question does that kind of, the fact that there's all these different rates of change, what rate of change would be special of all those?
The largest rate of change?
Maximum, right? Largest, right? Somewhere along here, and it looks like in the third quadrant, there's a maximum around here, right? Somewhere, so some kind of got the wrong view of it here. Somewhere here in that third quadrant, for angles between pi and 3 pi over 2, the rate of change is maximum. So we want to know where that is. And then there's another, would be another point of interest, another interesting direction where the rate of change is?
0.
Yeah, like where does it 0? Somewhere along here, because it's negative in some places and positive in others. Then somewhere around here, it's 0, like I'm trying to show there.
Where there's no change in z.
Right. If you go right, exactly. It's like if you're on the side of the mountain, you can imagine that there's a direction you would walk where you wouldn't change your elevation, like walking, around on a level curve, right? So let's try to investigate. Like, so what's the direction and magnitude of the max rate of change, and direction of 0 rate of change? Okay, so we're gonna work on that. Okay, so much more important than making sure you get every word on the slide down in your notes is that you're engaged, you're listening, things are making sense. You can always re-roll the video and take a really good set of notes later. So just make sure you're really engaged here and thinking about, if you are writing, thinking about what I'm saying and what you're writing. So we know this is our directional derivative. It's the gradient, right? The vector of the partial derivatives, dot the unit vector in the direction we want the rate of change. So that we derived last time. And this is simply, getting a change in z in a certain direction. And if we only go one in that direction, the unit vector, then that change in z will also be the rate of change. And that's where that directional derivative came from. Okay, and that's our notation. And so since it's the dot product, we have another form of it, and that's this one. Remember that the dot product of the magnitudes times the cosine of what? So what angle is that? Is that theta? Is it the same as theta? So what is this? This is the angle. What's the
Angle between the gradient and the unit vector.
Yeah, so it's the angle measure between these two vectors. Which is different than theta, right? Theta is our standard trig angle swept counterclockwise from the positive x-axis, right? It's our standard angle that we use for cosine and sine. So this, since it's the dot product of these two vectors, it's the angle between them when they're tail to tail. Okay, so what's the magnitude of the unit vector? What's that? Just 1. So we can rewrite the directional derivative or the rate of change as just the magnitude of the gradient times the cosine of the angle between our two vectors. Is it fair?
How is it 1?
Because it's a unit vector.
Magnitude for the unit vector is 1.
Okay, thank you.
Yeah, because that's to get the directional derivative, we had to have a unit vector. So its magnitude is always 1. Okay, and so then this gives us an alternate form for the rate of change in the direction of u. And this is going to unlock this question that we had about max rate of change and rate of change 0 and so on. So let's talk about that. So what is the
u parallel to the plane?
Yeah, u is in the xy plane, right? This is an R2 vector. Remember the picture I showed you with the...
Yeah, but u is parallel to the
Okay. Yeah, question.
I'm sorry, could you repeat what theta is?
It's the standard trig angle. The standard trig angle from the positive x-axis. Right? Cosine and sine, the unit circle. So it's the angle swept counterclockwise from the positive x-axis, just like you've been doing in trig for the last couple of years.
Okay.
Cool. All right, so now we're ready. We got this. Our directional derivative is this, and this is going to help us figure out what the maximum value is. So what's the biggest this can be? So we got this, the magnitude of the gradient, which really there's no flexibility there. And then we have cosine of alpha. Well, what's the biggest that can be?
It's going to be the magnitude of...
What's the biggest this can be? 1, right? We can't, that's so when we can get cosine alpha equal to 1 is when we can get the biggest directional derivative, and then like you were saying, that's going to be the magnitude of the gradient then, is the maximum value of the directional derivative. Okay, and then in what direction alpha does it occur? So what alpha gets us a cosine of 1? What alpha gets us cosine of 1?
0.
0, right? So what does that mean? If alpha is the angle measure between the gradient and u, and that angle measure is 0, then how do we pick the direction of u?
It's in the direction.
It's in the same direction, right?
Yeah, pick u to be in the direction of the gradient, right? So that will make alpha 0. So we make alpha equal to 0, and so we're going to make u the direction of the gradient. So this maximum rate of change is all about the gradient. The actual value of the max rate of change is the magnitude of the gradient. And the direction that you go is the direction of the gradient vector. So the gradient is like the key to this direction and magnitude of max rate of change of all possible directions.
And to clarify, the gradient is the partial derivative of x and the partial derivative of y as a vector.
Yep, right there. Remember? So that's a vector, right? So that's a vector. It has magnitude and direction. Its magnitude then, we've just shown, we just proved that its magnitude is the direction, or is the maximum rate of change. And then its direction of that vector is the direction of the max rate of change. Okay, so let's see it in the picture of that example we had. What did we say our partial derivatives were?
-2, 1.
-2, -1, right? So our gradient that we got from last time was gradient of h at 2, 2, at the point 2, 2, was -2, -1. And what did we say we thought the direction of max rate of change was somewhere in which quadrant?
The third.
Third, right? Is that pointing in the direction of the third quadrant?
Yes.
Yeah. So it's like -2, 1 is something like that. Meaning we want to go, for a x change of -2, y change of -1. So the ratio of changes -2 to -1 will give us the direction of max rate of change. Or if you're on the mountain, the direction you would go horizontally, that you would go up the fastest, right? The steepest ascent up the mountain. Okay? And so that's our direction of max rate of change is -2, -1. The gradient. That actual the magnitude of the max rate of change is going to be what? What do we say?
Square root of 5.
Yeah, it's going to be the square root of the magnitude of that gradient vector. It's all about the gradient when it comes to max rate of change. It gives the direction and magnitude of the max rate of change. Okay, what about the direction of greatest negative rate of change? What direction and magnitude would that be?
Opposite.
Would it be? Yeah.
So it's the exact same situation. It's along this trace of the surface, just going the opposite direction, right? So what direction is that?
2, 1.
2, 1. And then the rate of change will equal? Same, but z goes down now.
Negative square root of 5.
Negative square root of 5. So when you found the direction and magnitude of max rate of change positive, you have also found the direction and magnitude of greatest negative rate of change, which is just in the opposite direction and has the opposite value. All right, does that make sense so far? Now let's look over here at that direction relative to the contour plot. What do you notice about the direction of max rate of change, or direction of the gradient here in the relative to the level curves? Yeah, do you see this orthogonal? And why does that make sense? That it would be orthogonal to the level curve at that point. Because we're trying to get up the fastest. How would you get up the fastest if these level curves are giving us values of z?
That makes sense because the hypotenuse would be longer than, the other sides of a triangle.
Right. So we want the direction that heads to the next greater value of z quickly as fast as possible. And what would that be? That'd be going orthogonal to the contour lines or the level curves is going to get us to the next level curve the quickest. If you kind of go on an angle like this, well, it's taking more horizontal change to get up to that level of z. So that's going to be a lower rate of change. The fastest rate of change is take the most direct route to the next higher value of z. Well, that's going to be orthogonal to the contour lines. Likewise, the greatest negative rate of change will be in the opposite direction, also orthogonal to the contour lines. You want the direction that gets you to the next lower z as fast as possible. And that's also going to be orthogonal. All right. What about direction of zero rate of change? So if we go back to whoa, where'd that come from? That was weird. All right, so if we come back to our cosine alpha magnitude of the gradient as the directional derivative, how does this become zero? Zero when?
Alpha is pi over 2.
Or
3 pi over 2.
3 pi over 2. Pi over 2 or 3 pi over 2, which is what? That's orthogonal to these directions, right? So that's going to be pi over 2, and 3 pi over 2 will be like this. How does that compare to the level curves?
It's parallel.
Parallel or tangent to, which makes perfect sense, because what happens if you stay walking along a level curve? What happens to your z value?
Nothing changes.
Doesn't change. It's zero change, right? Zero rate of change because z is staying the same. So walking parallel in the direction parallel or along the level curve is zero change in z, so it's zero rate of change. So this is du h at 2, 2 equals 0 in this direction, 0 in this direction, positive square root of 5 in that direction, negative square root of 5 in this direction. Oops. Where are these? Oh, there it goes. Okay. Does it make sense? So, for greatest max rate of change, direction of the gradient, and the magnitude of that rate of change is the magnitude of the gradient. And what is the gradient? The gradient is a two-dimensional vector, right? It's a two-dimensional vector. So that is right there. That's the gradient vector right there. It's a two-dimensional vector that has just an x and a y component, which are the two partial derivatives. Okay, any questions on this? Zero rate of change, max, and max negative rate of change.
Why do we make it equal to 0 for the cosine change?
Because that's what we wanted. We were asking, how do we get zero rate of change? This will never be 0. This will have a value. So the only way we can get this to be 0 is if cosine alpha equals 0. So the premise was we want to figure out when the derivative equals to 0. So then we got to look over here and say, what makes this 0? Well, that's when cosine alpha is 0. Is that better? Okay. Other questions? Okay, so, and there's one more thing. So if we wanted there's still another angle. So we've talked about the angle theta and the angle alpha. Sorry, yeah, alpha is the angle between the unit vector and the gradient. Theta is the standard trig angle. And then finally, there's another angle. So let's do a rate of change here in the fourth quadrant. No, second quadrant. Let's do rate of change over here in the second quadrant. Let's go back to that 5 pi over 6 example. Or say that, what's that? That's about 3 pi over 4, say. So, no. Back a little bit, no. Stop. All right, got it. Okay, so say we're talking about the angle of 3 pi over 4. So 3 pi over 4, that's our angle theta. Here in the second quadrant. There is some angle alpha. So the angle alpha would be the angle between 3 pi over 4 and the angle for negative 2, 1. We don't really care about that here. So that's the angle alpha. So theta is 3 pi over 4, say. Alpha, we know what that is, don't care about it. So there's another angle. We're going to call it beta. Beta is like the angle of elevation on the surface. This is still a third angle here. And so if you were to walk, here you are on the mountain, and we want to walk in the direction of 3 pi over 4, you're going to walk up at some angle. That's what I'm calling beta. All right, so beta, you can look at a right triangle here. So this is like the change in z. This is the change along the unit vector. So it's not a change in the unit vector, which it's a horizontal change along the, so I'll put in parentheses, meaning horizontal change along the direction of the unit vector. So how would those changes then relate to angle beta? How could we bring together the vertical change in z, the horizontal change along the direction of u, and beta?
I'd imagine you would use the directional unit vector, right?
We want to bring together these three quantities, this angle measure, and this opposite side, and this adjacent side. Tangent, right? Tangent of beta would be opposite over horizontal change. But what's that? What is the change in z over the change in horizontal?
Would that be the directional derivative?
That's exactly what the directional derivative is. It's the rate of change of z with respect to going in that direction. That's our directional derivative, right? So beta would be the inverse tangent. So this is the idea that tangent is like slope, right? The tangent is the slope, and so is rate of change. Rate of change is slope in a geometry sense, right? So beta is going to be the inverse tangent of your directional derivative at that point. If it's for the max rate of change, well, you don't have to calculate, you don't have to use the formula for this. We know that the directional derivative or the rate of change, if it's maximum, is just the magnitude of the gradient. So you don't have to go through the formula for this. If you're talking about in the direction of max rate of change and you want to know the angle of elevation, then this is just the magnitude of the gradient in that case. Okay, so any questions on, that's finishing up directional derivative. Okay, here we go. So let's, I'm going to leave on. That's good? Okay. So now let's go back, and now let's just say this is any point, A, B. Not 2, 2 anymore. This is just going to be any arbitrary point, A, B. And then, so this point then would be the order triple A, B, H of AB. Okay? Now, this is kind of review, but I'm going to just deviate a little bit from AB in any direction, so arbitrarily. So just an arbitrary deviation from AB to a new point here, which I'll call XY. So XY represents any new point close to AB. Any other point that's just somewhere close to AB. And so if you change from AB to XY, your Z value of our function is going to change, right? Unless it's a horizontal plane. But if you deviate a little bit from AB to a new point, you're going to have some change in Z. Okay, so the exact change in Z would just be the final value of the function, the final Z value, minus the initial. But now I want to get a really good estimate using calculus. And this is review. So estimate of dz using calculus. Well, it's actually not an estimate of dz. So it's an estimate of this, and it is truly equal to dz. But it's an estimate of our change in z. Okay, so just kind of clearing the language there. So dz stands for the estimate using calculus. How would we do it? So how can we get, if we change x from A to x and y from B to y, how can we write out what the resulting change in z would be, or dz? We've done it before. So it goes back to, how do our partial derivatives give us changes in z? How do the partial derivatives give us changes in z?
Because it's tangent to the surface at that given point, right?
Okay, but so like how do we actually do it? How do we actually get it?
You take the partial derivative of, sorry, good.
You take the partial derivative and
then you see, you multiply it by the initial point, right? F of x, not y naught z naught, right?
You multiply by the initial point.
You multiply by dx.
You're right. So the whole point, this was our meaning for the partial derivatives, which is, given any change in x, we can get the corresponding change in z by multiplying by the rate of change. And so over the last 4 days of class, we've said this many times. Given any change in y, we can get the resulting change in z by multiplying by the... So if there's one thing about partial derivatives I want you to learn, it's this. That it's the multiplier that gives you the change in z for any change in x. So in that sense, it's telling us how fast z is changing with respect to x. And then you also have the partial with respect to y. It's similar for the change in y. So this is kind of like the most important thing about partial derivatives. And so now what happened? We just changed x and we changed y. How much did we change x by? What was our change in x from here to here?
X minus a.
Good. And how do we get the resulting change in z for that change in x?
Multiply it by the partial derivative.
That's it. At AB. And then how much did y change?
Y minus b.
And to get its contribution to the change in z, multiply by hy. H of y. And what do we do now with those individual changes to get the change in z?
Find the magnitude.
So I got the change due to the change in x, and I got the change in z due to the change in y. I want, yeah, you're just going to add them together because they're orthogonal directions. There's no overlap. There's no influence. They're totally exclusive and separate. So we can just add the individual contributions to get the total change in z.
This is vector addition.
No, these are all values. There's no vectors here. This is a partial derivative. That's a value. And then this is the change in x. That's a value. Okay, so this dz is called the differential. Does it give the exact change in z as we change from ab to xy?
If the change was, infinitely small, but
Yes, right. For really, really, really small changes, then it would be so close that we couldn't tell the difference. But still, technically not exact, right? This would be exact. Actually get the two function values and subtract. That's how much z would change exactly. But so why is it not exact? What is it about this way that makes it non-exact?
because the partial derivatives are changing.
Right. These equations assume that the partial derivatives are what?
Constant.
Right. These equations assume constant rate of change. Or linearity, linear. So if we're sticking to linearity while we're moving away, then we're going to begin to deviate from the actual surface if it's curved. So these are definitions here, these meanings here for partial derivatives are based on constant rate of change. Proportionality, right? Linearity. And so that's what this change in z is based on. So it's an estimate based on the fact that our partial derivatives are linear. They're linear, and so as you deviate away from AB, your point is going to start deviating a little bit away from the surface, and the further you get away, the greater chance that you could have large deviations, right? So this only really makes sense to do this when you're close to AB. All right, so let's do an example of the differential here quickly. We got 3 minutes. So that's called the differential. But the differential, I mean, we've already done it, right? We've already talked about have a change in x and a change in y and get the resulting change in z, okay? We already kind of did that concept. So we just keep coming back to the same thing. So where's that problem? Here it is. Okay, so a large block of ice, 4 by 4 by 1.5 feet tall. Something like this. So 4 by 4 by 1.5 feet. But it's melting. Okay, so it's melting, and so these are really changing quantities. So we really want to label this with changing quantities. So what should I use for variables here? Because the side lengths are varying. So what do we want to use here?
DL, W, and DH.
All right, you want to use H for the height?
You can use DS for the side.
And so it's not DS though. So I'm talking about the actual lengths of the sides. Those wouldn't be DH and DS. Those would just be H and S.
Oh yeah, HS. Sorry,
yeah, that's okay. That's okay. A couple of you said that, so I just wanted to clarify. All right. So here, this is really what's happening because S and H are varying as this thing melts. But then in a snapshot at the point we're interested in, we'll be looking at this particular case where S equals 4 and H equals 1.5. Okay, notice that the height decreases twice as fast as the lateral sides. All right, so that would mean that dH equals what?
2ds.
Does it equal ds?
2ds.
2ds, right? So for any change you have in the s, your change in height would be twice as much, okay? So now use differentials to estimate the change in volume. So we want to know what that is. But to get the change in volume, to get our differential equation for change in volume, where are those partial derivatives going to come from? They got to come from somewhere.
E equals s squared times h.
Yeah, they're going to come from a volume function of s and h, right? So based on a volume function of s and h, we can write the differential, which will have partial derivatives, right? So that's going to be s squared h. And so our v sub s is equal to 2sh. V sub h is going to equal
Square.
s squared. And so what's our dv then? dv will be vs times.
2
So how do we get the change in volume? It's going to be based on what? The rate times the change in side length plus, this is what we just did on the other slide, the rate times the change in side length or height. So this is our differential equation. And so we've got that for our changing situation here. And now we're going to apply it to this particular situation where h is 4, h is 1.5, and it tells us that the height decreases by 1 inch. What does that tell us?
h minus
dH is
1.
negative 1/12. If we're going to stay in feet, right? If we're going to stay in feet, then we got to make that foot into, or that inch into feet. And what would ds be then? Given this fact, our ds would be what? Half of that, right?
actually 124.
Based on, we know that changes in height are twice the changes in side length. So now we got everything and we can plug it in. We got v 2sh times ds plus s squared dh, and we have all of those. We have s, we have h. So we're going to take all those values, s, h, ds, and dh, and plug them in. And the resulting number will be how much the volume changes when the height goes down by 1. And will be estimate or exact?
Estimate.
Estimate, because the rate could be changing, right? So the actual rate of change could change as the height decreases. So it's just an estimate based on this snapshot of time.